So I'm going to look at this past paper question that came up in 2017, looking at a cubic function. In the first part you asked to just show that x equal to minus 3 was a root, and then to find the other two roots. To do that, you would just plug in minus 3 for x, and you would show that that resulting y value, or f of x, was equal to 0. That meant that the curve touched the x-axis at that point, minus 3. To find the other two roots, then you would use the fact that if minus 3 was the root, x plus 3 was a factor, and then you'd carry out some long division to work out the other two roots. For more on that, see the algebra section of the website. What I'm going to focus on here is the second part, which is to find the coordinates of the local maximum and local minimum point of the function. And I'm going to use the fact that we were able to find local maximums and local minimum functions by deriving the functions and letting that equal to 0. So the roots for this function are x equal to minus 3, x equal to minus a half, and x equal to plus 1. But this is just a quick sketch of the curve. We know that the root is here, minus 3, here, minus a half, and here, plus 1, by answering the first part correctly. Now you're asked to find the local maximum point and the local minimum point of the function. Well, at the local maximum and the local minimum, the slope of the tangent to the curve is 0. So I've just written that out there. At the local maximum or minimum, the f prime x is equal to 0. So what I need to do is just derive that function there and let it equal to 0 and solve the resulting quadratic equation. F prime x is equal to 6x squared plus 10x minus 4. Now what I want to do is I just want to let that equal to 0 and solve. So when you do that, 6x squared plus 10x minus 4 is equal to 0. Well, I can divide them all by 2. 3x squared plus 5x minus 2 is equal to 0. Then I can just factorize that. The factors are 3x minus 1 and x plus 2 equal to 0. So therefore the roots of that are x is either equal to a third or x is equal to minus 2. So we know they are the two values of x that give us a slope of a tangent to the curve being 0. So they are either the maximum or the minimum. Now, to find whether they're the maximum or the minimum, you could simply just plug in that value of x into the original cubic and see which gave you the higher y value, or else we use the fact that something else happens at the maximum or minimum. We're going to have a quick look and see what happens at this point on the curve to the slope. We know that at this point the slope is positive, at the green line the slope is 0, and here the slope is negative. So on going from the blue line to the green line to the orange line, the actual slope is changing from a positive value to a negative value. When we were able to work out the derivative of the function, we were able to find the slope. And if you work out what's called the second derivative, the second derivative tells you how the slope is changing. And if you've gone from a positive slope through to a negative slope, that means the slope itself is becoming more negative, and therefore the second derivative will always be negative. And at this point, when you're going from a positive value through to a negative one, well, you must have been at the top of the curve. So when the second derivative is negative, you must have been at the top, so that's a local maximum. Likewise, the opposite happens at the local minimum. So I've just written that there. The second derivative, which is written d2y dx2, is less than 0 when you're at the top of the curve, so at the local maximum, because the slope is changing from positive to negative. So the slope is getting more negative, okay, at the top. At the bottom of the curve, so the local minimum, well, if you look at that orange line there, the slope of that orange line is negative, the slope of the green line is 0, the slope of this light blue line is positive. So what's happening to the slope? Well, at the local minimum, the slope is changing from a more negative value through to a more positive value. So at this point, d2y over dx2, so the second derivative, is positive. It's greater than 0. So I'm just going to bring back in the original question to show you how we can use that fact to answer this sum. What I'm going to do is I'm going to find the second derivative of this function. So notice here I've called it d2y and dx2. That's when I write the function as y is equal to, where the first derivative is just dy dx. Here, because I've stuck with f prime x, I'm just going to say it's f double prime x is our second derivative. Well, that's going to be 12x plus 10. That is when I derive my first derivative again. Now I need to just plug in the values of x and see whether I get a positive or negative value into the second derivative. First value of x I had was x equal to a third. So 12 times a third plus 10 equals 14. So at this point, I know that d2y dx2 is positive, so therefore at x equal to a third, I must be at the local minimum. So let's just double check. At the other point, x is equal to minus 2. 12 times minus 2 plus 10 is minus 14. Minus 14 is less than 0, so i.e. the second derivative is negative at that point, so I must be at the local maximum. That is just another way to use derivatives, using the second derivative to find the local maximum or the local minimum. We just derive the function again, plug in the values of x that I want to see what's happening at that point, and see whether they're positive or negative to see whether we're at the maximum of the curve or the minimum of the curve. Another thing about the second derivative is we're able to work out what's called the point of inflection on the curve. I'll just zoom in on this. We know what's happening at this point in the curve here. We have a negative slope, and I know right here I also have a negative slope, but this negative slope is quite a steep curve, whereas this one here is getting closer and closer to 0. So the point of inflection on the curve is the point at which the curve stops bending in one direction and it starts bending towards the other one. We can find that point when we let d2y dx2, so i.e. the second derivative, equal to 0. When we're answering this question here, the point of inflection occurs when the second derivative equals to 0. That means 12x plus 10 equals 0. X is equal to minus 5/6. Okay, that just tells me the point of inflection in the curve. So I've gone through a leaving cert question based on applications of differentiation. We know now how to find the local maximum or the local minimum of the curve. We just let dy dx is equal to 0. Then when we want to find whether it's a local maximum or minimum, we can plug in that value of x into the original function to see which value is the highest, or else we can find the second derivative. The second derivative is negative at the local maximum because we're going from a positive curve to a negative curve, and the second derivative is positive at the local minimum because we're going from a negative slope through to a positive slope. And the last thing, the point of inflection on a curve, is when the curvature of the actual curve itself changes, i.e. it goes from a more negative value through to a more positive or vice versa. And that happens when the second derivative is equal to 0.